Hi, I'm Shanawaz. In this lecture, we'll see if we have, say, a map from the unit circle S1 to a space X. So, if this is a continuous map, so if this map H is null homotopic, then what will happen to the induced homomorphism? I mean, is that trivial or not? So, this is what we are going to check in this lecture. So we'll state this result in a lemma, that is if we have a continuous map, so let h from s1 to a space x be a continuous map, then the following are equivalent. So the first item is, so h is null homotopic. The second item is h can be extended continuously to a map, so h can be extended continuously to a map K from the closed unit ball to the circle, unit circle S1. And finally, the third item is the induced homomorphism H star is a trivial homomorphism of fundamental groups. So let us prove this. So first we'll prove first implies second. So let us take H to be the null homotopic map. So let H from S1 to X be null homotopic. Now, by null homotopic, we mean it is homotopic to a constant map. So, if this is null homotopic, so there must exist a homotopy. So, let H from S1 cross 0, 1 to X be a homotopy between H and a constant map. That is, if we restrict H in second coordinate to 0, then we get the map H of S. This is true for all S in the circle S1, and H of S1 is the constant map for all S in S1. Now this is what we are given. Now let us consider a map. So let say pi be a map from the unit cylinder. So this is actually a cylinder of radius 1 and height 1 to B2, where B2 is the closed unit ball. So let this be a map defined as, so this pi of st is 1 minus t times s for all t in the interval 0 1 and s in s1. So let us see what we are given. So this s1 cross 0 1 is actually a unit cylinder. So we have this cylinder over here. So the radius of the cylinder is 1 and the height of the cylinder is 1. So here we have a map pi from this cylinder to the unit disk. So let us suppose we have the disk B2. So this is, I'm sorry, so this is B2 and we have this map pi here. Now what pi does, so when we take t to be 0, we get s. That means when, so this is the direction, so this is the direction t over here. So when t is 0, we are giving input to the point is from this circle, so we get s back. I mean we get the boundary of this ball here. So this is actually the unit disk. So when t is suppose half, so we are giving pointers from this circle, so we get a circle over here of radius half. So finally when we give t, I mean when we put t to be 1, that means we are giving input from this top here. So this, then we get the point 0. This means this pi collapses this circle to the point 0. So this is and this is here s1 cross 1. This is s1 cross t naught. Suppose this is at time t is equal to t naught, or we can view this map as, so I mean suppose this is the point b naught here. So suppose b naught is here, pi of b naught. So when we give these values, so when we give these values as input, so we reach from this point pi of b naught to 0. Similarly, if we give these inputs, suppose this point corresponds to this point over here, then this vertical line corresponds to this line over here. So one can note this pi is, so let us write this down here. So note that pi is continuous it is also closed and subjective. Closed and subjective. The subjectivity of this map is visible from this diagram over here. It is also closed because it map is the closest. So hence it's a quotient map. So it is a quotient map. So one can note that this pi uh, note that pi collapses the circle S1 cross 1, which is this circle, to the point 0, and otherwise it is injective. Now we will use a result from quotient topology, which is like this. So let us write this down over here. So the result goes like this. So suppose we have a space X here, and let us suppose P be a quotient map from uh, X to Y. So this P is given to be a quotient map. And suppose Z is some other space and G is a map between X and Z. Now if this P is such that G is constant at the set P inverse Y, where Y is in Y, then this map G induces a map from the space, so this space Y here, from this space Y to Z. Let us call this map F, such that G is same as F composite P. That means this diagram commutes. So this is property of quotient maps. So the only thing we need over here is that this G has to be the constant at P inverse Y, where Y is in Y. Now one can note over here uh, this pi is given to be the quotient map, and we have a homotopy H from S1 cross I, S1 cross interval 0 1 to the space X, which maps, which is a homotopy between edge of S1 and the point, say some fixed point here. So this is edge of S1. So this is the homotopy here between this loop and this constant map. Now since this H is constant on the inverse image of this point, and since this pi is injective otherwise, so this H will induce a map. Let us call this map k from b to x such that this diagram commutes. So mm, now there is this uh, condition over here that if g is uh, continuous, then this f is also continuous. Now in our case, h is given to be continuous, so k has to be continuous. So since h is, so let us write down over here, since h is constant at the inverse image of this point, which is s1 cross 1. Therefore the map h induces, so therefore it induces a continuous map say k from the ball b2 to x such that this diagram commutes such that k composite pi is the map h. So this induces a continuous map k. We'll forward to mention over here via pi such that k composite pi is h. That is h of st is k composite pi of st, but k composite pi of st is just k of 1 minus t times s. So this is true for all s in s1 and t in the interval 0 1. So this implies, or so therefore h of s the same as h of s0, because h is a homotopy between the map h and the constant map. So h of s0 is just uh, h of s. I mean, actually this is the map. This is k of s. So let us, I mean, if I put t to be equal to 0, we get k of s is actually uh, or let us write this way, k restricted to the interval h s1 cross 1 is k of uh, so it is k of uh, let's call this t to be 0, so it is k of s, which is h of s0, but h of s0 is same as h of s. So this means this is true for all s in s1. So this means that when we restrict k to this circle over here, I mean when we restrict k to this circle over here, we get this loop over here, that is edge of s1. So that means this k is an extension of the map h. So that is uh, I mean, this shows that K is a continuous extension of the map H. So hence this is done. Now let us prove the item second implies item third. So we'll assume that the K is continuous extension of the map H. Then we'll prove the H star is a trivial homomorphism. So let K from B2 to X be a continuous extension of the map H, uh, which is a map from S1 to X. Now let us consider, so let I from S1 to B2 be the inclusion map. Now one can note here, since K restricted to S1 is just the map H, we have K is nothing but the composition H composite I. So here we have I, which is a map from S1 to B2, and from B2 to X we have the map H. Now look at this uh, composition over here. So we get a map from S1 to X, which is just the map H. Not H, is K over here. So we have K composite I to be the map H here. Now, so therefore, the induced homomorphism H star is same as K star composite I star, where I star is the uh, induced homomorphism from the fundamental group of S1 B naught to the fundamental group of B2 B naught. But the fundamental group of S1 is the group of integers, and that of B2 is the trivial group because B2 is simply connected. So since fundamental group of S1 based at B0 is isomorphic to Z, and fundamental group of B2 based at B0 is isomorphic to trivial group, we know that this I star is the zero homomorphism. So therefore I star is the zero homomorphism. Uh, Hence, so this shows that K star and hence H star is a zero homomorphism. So if this I star is zero homomorphism, therefore K star is zero homomorphism, and hence H star is zero homomorphism. So this shows that K star hence H star is the zero homomorphism. That is, H star is trivial. This proves uh, second implies third. Now finally let us prove third implies first. So let P from R to S1 be the standard covering map. Be the standard covering map. That is, so let us move to the next page. So first we erase this. So that is this P, that is P of x is just cos of 2 pi. I mean, this is cos of 2 pi x sine of 2 pi x, while this x is a real number. Now let P not be the restriction of P to the interval 0 1. So be the restriction of P to the interval 0 1. That is, P naught is just the restriction of P to the interval 0 1. So one can note that P naught is a loop in S1 based at point B naught, which is the point 1 0. So note that this P naught, because if we have this circle over here, let's say this is point 1 comma 0, that is called this point B naught. So this loop, this P naught starts at this point and ends at this point, because P naught is a map from interval 0 1 to, so when you put the point 0, you get B naught, and when we put the point 1, we again get the point B naught. So this is a loop. So note that P naught is a loop in S1 based at point B naught, which is the point 1 comma 0 in S1. Now since the fundamental group of the circle based at point B naught is isomorphic to Z via the homomorphism, let us call that theta. So theta is the homomorphism from the fundamental group of S1 B naught to the group of integers. So this is defined by, so when we computed the fundamental group of circle, we defined this map there. So this is defined as, so when we uh, operate theta over the homotopic class of a loop sigma, we get sigma tilde 1, i.e. the endpoint of it is left, while sigma tilde is a map from 0 1 to R is the lift of sigma, which is a loop in S1. So the situation here is like this. So this is our real line, and this is the circle S1 here. This is the covering map from 0 1 to sigma. Sorry, S1 we have the map sigma, and this is the lift of sigma, which is sigma tilde. So theta maps the homotopic class of sigma to the end point of its lift. So that means this theta will lift the homotopic class of this p naught to the end point of p naught, which is 1. So therefore theta of the homotopic class p naught is just the end point of its lift. Let us call that p naught tilde. So that will be p naught tilde of 1, which is 1. Where? Because this p naught is a standard loop, so it starts at point 0. I mean, this p naught is a standard loop, so this p naught tilde will be a path in R which starts at point 0 and ends at point 1. So where p naught tilde, which is a path from which is a path in R, and is a lift of p tilde, is the lift of p naught. Now one can note here, so this I mean the homotopic class of p naught tilde is carried out to 1 in Z, where 1 is the generator of the uh, this group. So therefore this homotopic class of p tilde will be a generator of this group over here. So since 1 generates the group Z, therefore the homotopic class of p naught generates the group uh, the fundamental group of S1 based at B naught. Now let us take a point. So let x naught be a point in X such that x naught is h of B naught. So one can note here this h is a map from S1 to X. So h of B naught will lie inside X. So now H composite P naught. So H composite P naught will be a map. So P naught is from interval 0 1 to S1, and H is map from S1 to X. So this H composite P naught will be a map from 0 1 to X. So when we look at H composite P naught of 0, so that is same as H of P naught of 0, but P naught of 0 is same as uh, H of B naught, and H of B naught is X naught, because P naught of 0 is B naught. Uh, so this X naught is same as H of B naught and this h of b naught is same as p h composite p naught of 1, because p naught of 1 is b naught. So this means the composite map h composite p naught is a loop. So therefore the map f, let us call this f, which is the composition of these two maps. So this is a loop in x based at x naught. But the induced homomorphism, so this is called hypothesis, which is this is not just a homomorphism from the fundamental group of S1 based at B naught to the fundamental group of X based at point P of B naught, H of B naught, which is X naught. So this is based at X naught. So this is the trivial homomorphism. Therefore, H star of the loop based at F, because this is a loop in S1, not in S1. So this is, so P naught. So this is a loop in S1. So it is mapped to the homotopic class of H of P naught, which is the homotopic class of F. So this since this H star is trivial, so this homotopy class over here represents the identity element of, so this represents the identity element of the fundamental group of X based at X naught. Now so therefore there is a path homotopy between there's a path homotopy, say f, between the map f and the constant path at x naught. So therefore there is a path homotopy, say f from interval 0 1 cross 0 1 to x between the map uh, between the map between the path f, which is the composition path h composite p naught, and the constant path at x naught. So we have this homotopy over here from, so this f is a map from this interval 0 1 cross 0 1 to the space x over here. So this is the map f. So this is the loop f, which is based at x naught. So this f is homotopic between this loop and this constant map. So we have this homotopy over here. So now note that the map so if we look at the map p naught cross id on 0 1. So this is a map from 0 1 cross 0 1. Now this is the map from this p not the map from 0 1 to s1, and this ind map on 0 1 is a map from 0 1 to 0 1. So this is the unit cylinder. So we have a map here, p naught composite 0 1. Now this p naught, now what this p naught does to interval 0 1, so it maps it to a circle, because p naught is a loop, standard loop on the circle. So, and this int map is the interval 0 1 to 0 1. So if we have this interval 0 1 here, so we get this cylinder over here. Now p naught of 0 is b naught. Suppose this is the point b naught, then this map is this line to this line, and this line again to this line, because p naught of this line is b naught, and p naught of the points on this line is again b naught. So these two lines are mapped to this line on the cylinder. So this map is the quotient map. Now why this map is the quotient map? Because p naught is closed, continuous, and subjective. Similarly, this int map is closed, continuous, and subjective. So this is the quotient map, since both the maps p naught and the int map on 0 1 are continuous, closed, and surjective. Now one can note that this map is these points to this line. Now these points, they are the set s1 cross the point 0, and this is the set s1 cross the point 1, and this line over here, this is the set s1 cross the point b naught. So one can note that this map is the line, these two lines to this line, and otherwise it is injective. So also p naught times the int map on 0 1 maps the sets s1 cross 0 and s1 cross 1 to the set s1 cross b naught. That means the inverse image of this line under this map are these two lines, and on these two lines the map f is the constant map. So this will induce a map over here because of this quotient map which we just mentioned while proving the other part. So this maps these two lines to this line and is injective otherwise. Now since f is constant, now since f is constant on the sets s1 cross 0 and s1 cross 1, because this f is a homotopic. These two lines are mapped to this point over here. So therefore this map h, this map f will induce a continuous map, say h from this cylinder, and so this is the cylinder S1 cross interval 0 1 to x over here. So hence hence f induces continuous map h from the cylinder to the space x, where the map p naught times the identity on 0 1, such that the composition h composite p naught times identity on 0 1 is same as h. Now what do we have to prove? We have to prove h is null homotopic. Now we'll so this is the map f over here. So we'll prove that this h serves a homotopy between the map small h and the constant map. So this induces, so therefore h h of p naught of s comma 0, so this is same as h of h composite p naught times identity on 0 1 of s comma 0, because when we operate this map over this point s comma 0, we get p naught of s comma 0 followed by the map h, but this map is same as f of s0. F of s0, since f is a homotopy between f and constant map, so this is f of s, but f is same as h composite p naught, so this is h of p naught of s. So that means this h of p naught of s of 0 is h of p naught of s. That means, so hence h of, so if we replace this by s, we get the map h of s, or when we restrict h to the set s1 cross 0, we get the map h. Similarly, h restricted over s1 cross 1, so we get the constant map at x naught. So this shows that this h is null homotopic. So hence h is null homotopic. So this completes the proof of this theorem.